So I would like to, first of all, kind of finish what I started on Friday. And I had to plan to talk about something slightly different later today. But let's first of all go back. And actually, John just introduced the toner and two equations. So let's finish this the lecture I gave. I started on Friday on showing you one way one can actually derive them from a microscopic model. So we started on Friday with a model that it's sort of a continuous time version of the V-check model written up there. So point particles, self-propelled along an axis E hat with the self-propulsion speed V naught. They align with their neighbors at a rate gamma, and they have rotational noise of rate dr. So the model, the microscopic model, contains these parameters here, the rotational noise dr, self-propulsion speed, the alignment strength, and if you like also the number density, the number of particles per unit area, which is kind of hidden in the equation, but it's obviously there. We went from the Langevin dynamics to the noise average dynamics for the probability distribution of finding a particle at position r with angle theta and time t. That's the equation written up there. And we made a number of assumptions here. We assumed low density. And we also assumed there's a really point particle and assumed the interactions was a spatial delta function. The second assumption, this assumption is not crucial. It's just a simplifying assumption. But the low density assumption is important. You wouldn't be able to proceed without that. And that goes along with what John was saying. If you write down the equations in general ways on the basis of symmetry, that's very nice. The equation is very general, but it has undetermined parameters. If you derive it from a microscopic model, you have to make assumptions. The structure of the equations, of course, that you will obtain will be the same, because after all, those are supposed to be general equations, but the parameters you will calculate will be model dependent and will depend on the assumptions you're making. So that's our what I call the Smoluchowski type equation. And what I started to do last time is essentially taking angular moments of these equations to actually derive the toner two equations. Now I'm going to change the notation a little bit, because it is true that the most compact way to do the derivation of the moment equations is to use this angular Fourier transform I introduced last time, where the moments are actually complex. But perhaps it has two problems. Number one is not the most transparent way from a physical point of view. And number two, it has the additional problems that the angular moment that I call psi k, psi 1, psi 2, have the same notation as what I use for the reduced distribution functions, the one particle, two particle distribution. And so I realized that that was confusing. So I'll actually go back to actually use, I won't use this complex notation, although it's actually very convenient if you actually want to do these derivations. So let's take the moments of these psi. OK. Now, of course, for angular moments, so the first moment, I just integrate over all angle psi itself. And of course, what I get is the number density of particles at position r and time t. OK? So the first moment is the number density. And this is a very special quantity for this system, because it is a conserved quantity, as John also described. The second moment, I multiply with this unit vector E, which depends on angle, and I take the average. And this quantity, last time I called it rho P, and I called P polarization. I'm actually going to call it W, the whole quantity. And so it's a polarization density. W is a polarization density. Or if you were to multiply by V naught, it will actually be a momentum density. If you like, P times V naught is what John called V, is a velocity for the system. OK? And the reason I change notation is because my P and my rho look awfully similar. So let me call it W. Again, I realize I could go on, take more moments. The next moment, and this would be an exact expansion, like the angular Fourier expansions of psi on the basis of this angular function. So the next one will be, I take the moment with E alpha, E beta, and I'm in 2 dimensions, so minus 1f delta alpha beta. And this, of course, is a rank 2 symmetric traceless tensor, which I will call Q alpha beta, which is actually called the alignment tensor and is the quantity you use as the order parameter for systems that exhibit nematic symmetry. Because, for instance, the x components of this W is proportional to the mean of cos theta, the xx component of this alignment tensor will be proportional to the mean of cos square theta. And so this will be if you have nematic order, this will be 0, but this will be non-zero. And so on. You can write the equations for all the higher order moments. Yes? Probably no. No, I don't. Sorry. All right. I'll change it when I. So, well, we should change it. If I can get the thing down. Of course not. I had written it down, the Fourier transform, so then I. All right. Okay. So, no, it's on. Well, let's try. I can also speak more loudly. Anyway, so we can transform the equation in equation for all these moments. But the idea here is that we want to close the equation, so obtain a closed set of equations. And we are actually going, so I'm going to point out that these fields, there are some that are actually spatial, and we are going to keep in our wavelength, long wavelength, long time description, our hydrodynamic description. So the density is a conserved field. That means it decays slowly, in the sense that the decay rate of the density, as John showed, satisfies a conservation equation. So the decay rate of a density fluctuation actually goes to 0 along wavelength, so that's a slow field. The polarization, I will call this polarization not velocity, I'll show you in a minute, although this quantity is really bought. The polarization is the order parameter of this system. It's the quantity that becomes non-zero in the state where the orientational symmetry is spontaneously broken. And so we actually expect that this quantity will also decay slowly near the phase transition. So these two quantities are the two quantities for which we expect to be slowly decaying and for which we want to obtain these continuum hydrodynamic equations. All the other moments are sort of fast fields in the sense that they all decay on microscopic time scales, in fact, on time scales of the order of this 1 over this dr over here. On the other hand, so there are fast degrees of freedom. On the other hand, and so the approximation we're going to be making is to write down these two equations, write down the equation for this quantity as well. But in these equations, actually, let me just kind of at least write the first two. So let's take the equation and take angular moments. First of all, we integrate over theta. Of course, we get dt rho, the first term. Second term vanishes. The next term is going to give us the divergence of V naught W. And the third term vanishes because there is a derivative in front of it. And so here we just obtain back our conservation equation for the density. Let's multiply now for a vector, a component of the unit vector E, and integrate the second equation. Second equation, we get dt W alpha. Let's write it in component. Next term gives us a OK, now it's minus dr W alpha. That's why I write the minus sign wrong over there. The gradient terms, we can bring the derivative under the gradient. So we get a minus gradient of d alpha of rho. Actually, we're going to get two terms here, because when we multiply with E alpha E beta, we're going to get Q alpha beta plus a contribution from this term. The contribution of this term gives us a minus V naught over 2 gradient of rho. And then we have a minus V naught derivative with respect to beta of Q alpha beta. And then we have to deal with this interaction term. Yes?
It's the gradient and the alpha.
Sorry. And then we have to deal with this interaction term. That's definitely more easily done in Fourier space, the way I did it last time. And I'm just going to write down the results. You can do it that way. You're going to get two terms from there. The first term is gamma over 4 pi. Notice that the term has no spatial gradients. It has angular gradients, but no spatial gradients. Rho W alpha minus gamma over 4 pi Q alpha beta W beta. And that's a whole equation. And finally, you get, let's write one more, or at least schematically. We get dq alpha beta. Now we get a minus 4 dr q alpha beta plus other terms I'm not going to write. OK, I'll just write 1 over here, which is gamma that comes from the interaction, gamma over 2 pi, w alpha, w beta minus 1f w square delta alpha beta. OK? And again, other terms containing interaction as well. OK, so that's the structure of the equations. Everybody see why we get this? OK. So yeah, we are happy with the first one. Clearly here, we need to eliminate q alpha beta, and then we'll have equations for higher moments over here. OK? Yes?
So the dot includes terms that involve higher moments?
Not necessarily. I just don't want to write them. Some of them, like here, there is a term that is going to involve a third moment. But there are also some terms that involve lower moments that I'm not writing. I just don't want to write it, OK?
But the point,
but among other things, here, there is a third moment.
I'm just trying to say, the thing that stops you from doing this exactly is that every equation involves, among other things.
That's right. So last time we were doing this in these angular Fourier components, which is actually nice, and it shows exactly how the equations are coupled. But I think this is a bit more physical. That's why I'm doing it this way now. So now we need to make some approximations. And the approximation we're going to make, first of all, let me just tell you, and then this actually can be made systematic. So we notice, so this moment, as all the other ones, actually decay. There's this term that says that they decay on times 1 over r, 1 over dr. So we are going to assume that we are interested, we're going to say that we are interested in time scale larger compared to 1 over dr, and we are going to neglect in this equation the time derivative of q as compared to this term. Okay? In addition, we are going to neglect, we're going to set all moments, all higher moments, simply equal to 0. We're just going to neglect them. Okay? That means that this term here that I didn't actually write goes away. Yes? OK. So first of all, look at this equation. This quantity, fluctuation in this quantity decay like gradients at least, actually gradient square eventually, right? So the decay rate of this quantity will go like q square in Fourier space. That means a long wavelength, the decay rate is 0. This is a slow quantity. All these other quantities in principle have these finite relaxation terms. If you were to solve it, if you just had this will decay exponentially over time 1 over 4 dr. Okay? So let me first of all look at this equation. So if I'm interested in time scale large compared to 1 over dr, I can actually neglect the time derivative compared to this term. I say this is small compared to that. And then I actually set this equal to 0. And then I solve this equation for q alpha beta in terms of lower order moments, because this is also coupled to the third moments, by that I'm setting equal to 0. Okay? Now, yes? I'm saying the second moment is a fast field, and all the higher moments are also fast fields. Okay? Now, why am I not neglecting this? This also has a decay rate here. What I'm going to because I expect this to be slow near the phase transition, because is the order parameter. And in fact, what I'm going to show to you is that when I actually substitute this q in here, this term will generate a term linear in w that will make the relaxation rate slow near the transition. Okay? So again, I neglect all moments higher than the third. I do this approximation for q. I solve the equation. I substitute in here. And I get to close the equation for rho and w. And now I just want to write down these equations to show you what they are, which are actually pretty much the equations that John had written down, even though I'm calling things w instead of v. So the first equation, of course, is the conservation law for the density. And the equation for W, let me now write it in vector form, as the following form. My alpha and beta are actually opposite sign as compared to John, but bear with me. OK, so these are the equations. And now let's compare them to what John, well, first of all, I'm glad John already told you about them, since a lot of the terms I don't actually have time telling you about. But all these parameters here, alpha, lambdas, and so on, are given in terms of the parameters of the original model. I'm not going to write them all down, but I want to write down these two. OK, alpha rho is dr minus, let's see, gamma rho over 4 pi. And beta is gamma square divided 32 pi square dr. OK? So what I found, so first of all, the equations, this is sort of what John called the Navier-Stokes-like equations. Although it's a little bit different. It's really, as he pointed out, a combination of Navier-Stokes equation with the equation for the dynamics of an order parameter describing actually a continuous phase transition. John told you about the meaning of these sort of convective terms, lambda 1, lambda 2, and lambda 3. Now, this quantity W here really has a dual interpretation here of a momentum density or a velocity field, if you like, and the polarization, which is really the order parameter for this transition. And in fact, this piece of the equation that John described in terms of friction and saturation of velocity can also be thought of as arising, although we didn't obtain it that way, and this is not an equilibrium system, but we could also think of this term as coming from the derivative. Let's write it as 1 over xi. Xi is some kinetic parameter. The derivative with respect to W of a free energy. And your free energy will have, that you will write down, as the typical 5-4 free energy. That would give you a continuous phase transition at the place where this alpha changes sign. So this alpha changes sign at a particular density or a particular value of the rotational noise. And this term can be thought of as the derivative of the free energy. This is your usual 5-4 free energy, if you were to plot it as a function of W. If alpha is positive, it has just one minimum at W equals 0. That would be the disordered phase. If alpha is negative, it has two minima, two equivalent minima, at some finite value of finite W of W, and that would be the disordered phase. So if we think, first of all, about the homogeneous solution of these equations, of course, the density has to be constant. And then the homogeneous solutions are just the one that set this term equal to 0. There are two homogeneous solutions. One is the disordered state, where W is 0. And the other one is the ordered state, where W has a non-zero value, which is determined by minus alpha over beta. Okay? This will be our ordered state or flocking state for the system. So we have actually derived the mean field model of the flocking transition, if you like, here. And the transition occurs at alpha equal to 0, which, if you like, defines a critical density that goes like the rotational diffusion rate divided by the alignment strength. And so the system can be ordered at high density or a low noise. You can actually get the transition by tuning either one of these quantities. Yes.
So, because W naught squared is minus alpha over beta, so one of them has to be negative. Alpha and beta will have the same sign.
Say it again.
So if like alpha and beta over there will have same sign, right? If they have opposite.
Yeah, that's,
So-
that's the first case she showed.
Let me do it. So let's look at the homogeneous steady states of these equations. Okay, the homogeneous steady states are the solution of alpha rho minus beta w square times w equal to 0. Clearly, rho is some constant rho naught. Okay, and then w is the solution of this equation. First of all, this kind of equation, you've seen it before many times because this is just the equation you solve when you do a mean field 5-4 equation that describes a continuous phase transition, okay? This equation has solution w, I'm just going to write it as a scalar. This is the magnitude of w. W equal to 0, which is always a solution no matter what alpha. It has an additional solution, which is w equal to actually plus or minus the square root of minus alpha over beta, provided alpha is negative. When you ask yourself whether these are minima or maxima of the free energy, when you, or actually in this case I should say whether these are stable or unstable solutions of these dynamical equations, you will find that this is the stable solution when alpha is positive, and this is the stable solution when alpha is negative. Okay? So when alpha is positive, we have a disordered state. And when alpha is negative, we have an ordered state with broken orientational symmetry, spontaneously broken, and that's your flocking state. The critical value of alpha when the transition occurs, according to this microscopic model, is 4 pi dr divided by gamma. Gamma is the alignment, and dr is the noise. Sorry, the critical value of the density when the transition occurs. So you can get an ordered state either at high density or low noise by tuning the noise or by tuning the. Probably wrote it wrong. Yeah, okay. Okay, I don't really want, one more thing I wanted to point out. Let's actually switch these boards again, because this will, something I'd like to come back to. As I said, all the other parameters have expressions in terms of the original microscopic parameters, but I'd like to point out one term, which is this one. In John's equation, this term was the gradient of the pressure that then phenomenologically expanded. That's indeed what it is here too. This is the gradient of the pressure. And actually, if you multiply this by V naught, okay, I will show you a little later, and if I forget to do it, please remind me, that this is exactly the gradient of the pressure of an ideal active gas. Because the pressure for an ideal active gas comes out essentially to be rho V naught square, so up to some factors that account for sort of like an effective mass, divided by 2 mu dr, where mu is the mobility of the system, and dr is actually the rotational diffusion rate. So this term indeed is the pressure, and you can actually do better. You can actually calculate corrections to the ideal gas pressure. This has been done, and get higher order terms here that describes the pressure of an active system. Okay?
So you get pressure even in the absence of noise?
The noise is here. This is noise averaged. This is noise averaged. So the noise is there, okay? Yes?
So this is because you didn't add like the ideal gas.
This is true, because I have no, these are point particles. That's why I have only the ideal gas pressure. Yes, absolutely. But it's possible to actually add the steric effects and do a lot better than this. But
also as in equilibrium, because if you have interactions, if the density is low enough, both particles are really close enough to interact.
this is true. But I think it's an interesting point that this indeed is the ideal gas pressure. And that depends on V naught, by the way, because, just a second, why does it depend on V naught? Because this is what people now are calling the active pressure or the swim pressure. If you have, what is the pressure? It's force particles exert on a wall. If these particles are swimming or moving with velocity V naught, right, they will actually transport propulsive force, which will cause pressure on the walls. So this is an intrinsically kind of active pressure that replaces, in this case, the ideal gas pressure. Sorry.
In the equations that John showed us,
Yes, I did not include it here. That's order W cube, so I did not include it here. You can derive that too, but I just didn't do that. Yeah, you have to go a little bit beyond what I've done here, but it's possible. Yes. So these equations are noise averaged. The noise term in his equation, after all, is added by hand. So I'll answer that question in 1 minute. Any other question? Yes. Because this linear density, because this is the ideal gas pressure. I have no repulsive interaction. These are point particles. This is an ideal gas of active pointers, as John calls them, that only have some alignment interaction. If I actually include steric effects, I can actually calculate the pressure beyond the ideal gas limit, and then it will depend on the higher power of the density. So that's why the reason, I mean, what's the density of an ideal gas? Is rho kT. And this is rho times what you could actually think of as an effective temperature for this system in this low density limit. Well, as we saw, by aggregating, what you mean? You're talking about the phase separation and that kind of effects that occurs. Yes, that's correct. I'll tell you about that next. Yes, okay. So I just want to make, yeah. So, yeah, that term was cubic in W and quadratic in gradient. I think to get that term, you have to actually go a little bit beyond this truncation that I made. And in fact, this truncation can be made, let me just say, this truncation can be made systematic if you are near the phase transition. You can actually identify small parameters, and this has been done and so on. So I would then say that term, in my opinion, doesn't matter near the phase transition. It may matter in the order phase, where actually you should really be using a slightly different truncation, which will actually generate that term. Right. Well, near the transition. Would you agree that term will not matter near the transition? But you never looked near the transition, so I would argue that term is not important near the transition, which is where this truncation I'm describing here actually applies. Yeah. And this can be actually shown systematically, that it applies there, and that is a systematic actually truncation, not just ad hoc the way perhaps I made it sound here. Okay. So let me just make 2 comments. First comment is that this same method, so it's absolutely true that these equations, I said all these parameters are given in terms of the original parameters, so this is model dependent, but the structure of the equation is very general. Any system with ferromagnetic, any flocking system, active system with ferromagnetic type symmetry will be described by this kind of continuous equation. Furthermore, this method can actually be used to derive equations for other systems, and has been used for deriving equations for systems with different symmetry. For instance, active particles that have only nematic interaction. They might align, but unlike the V-check particle, don't align head-to-head and tail-to-tail, but align regardless of head-to-tail, perhaps because the particles themselves are not polar, don't have a head and tail. This method has also been used to actually derive continuum equations for a different system. So one question you could ask is the following. A V-check model, after all, has this alignment rule. You look at your neighbors and align with them. What about what I would like to call more physical interactions, say steric repulsion? Suppose you had rods that are self-propelled and have a finite size. and they interact with each other only through steric repulsion. Okay? But we know that passive rods form nematic liquid crystals. They do break orientational symmetry, but they form states with nematic symmetry, not ferromagnetic symmetry, meaning there is orientational order, but this direction is the same of that direction. So what about self-propelled rods with only steric repulsion? Do they form a polar flocking state, or do they form a nematic state with some strange new non-equilibrium properties? And this question actually has been answered. The answer is the latter. They form a nematic state with strange non-equilibrium properties, and I'm not going to have time to tell you what they are. But this question has been answered by using this kind of methods, as well as by using numerical simulations, obviously, which have confirmed actually the calculation. So I'm telling you this to say that actually these methods can be quite useful, and I think it's really great to actually come to the problem from both ends, from the microscopic and from the phenomenological sort of generic point of view, and see that you learn really from coming from both sides, in my opinion.
It's also nice that they got the same answer.
Well, that's also true. Now, the other thing I wanted to say, and this actually goes back to a question that was that, is that there is actually another way. I went through this business of the Smoluchowski equation. There is actually another, well, there are many other ways, but there's at least one other way I want to mention of deriving this kind of equations, which is actually what you do. Instead of deriving an equation for the noise average probability distribution, which is what I did there, you can actually derive an equation without averaging over noise. So the equivalent of, say, my Smoluchowski equation, but without averaging over noise, and that will contain a noise term. And if you take that equation, but that noise term will be multiplicative. If you take that equation and expand it about, neglect the multiplicative nature of the noise, then you will have equations, continuum equations with noise the way John had written them down. On the other hand, that noise is very complicated, because it's multiplicative, and it's really very hard to do a lot with it other than throw away its non-multiplicative nature. And if you take the average of that equation, then you recover the equation that I've written here. But that's quite nice work, and so I want to give you the reference. It's a work by David Dean, quite some time ago. Is Journal of Physics A, 29, 613, 1996. And it's a nice method for deriving an equation that actually contains the noise. So you go from the Gaussian white noise at the microscopic level to a non-multiplicative noise at the level of the probability distribution. Okay, so if somebody's interested, they can look at that. This is about all I want to say about the two equations, because I think John will spend quite a bit of time talking about them. Just one thing that he may not discuss so much, since he's mostly probably going to discuss the properties of the order state, is the fact that actually after identifying the homogeneous state, you could actually go and look at their stability by expanding for small fluctuations about the homogeneous states. And what you actually find is that there is an intrinsic generic instability of the order state that actually sets in right at the transition. And so the actually order state near the transition, the uniform order state, where everybody is moving in the same direction with the same velocity and so on, that state is actually intrinsically unstable, and it's unstable at a well-defined wavelength in the direction parallel to the direction of broken symmetry. And what that indicates is actually the onset of a more complicated flocking state that's been seen actually in many, many simulations, which is a state of sort of bands of high density and low density region, which actually are traveling in the direction of the broken symmetry. So story is much more complicated. This only scratches the surface. These equations are very, very rich, and John will tell you a little bit about their behavior. Are there any more questions? Because I am going to kind of switch gear and actually try to address a little bit the question that I think Michael brought up about steric effects. Okay, if not, I will erase some of that in a minute. But let me, so what I actually want to tell you for the rest of today's lecture is about dense active systems. And indeed, I want to talk about the interplay between activity or cell propulsion and steric interaction, excluded volume effects. And I will do that, though, in an even simpler active system, which is I'm not going to think about rods or about elongated particles that can order in states with broken orientational order. I'm just going to consider, actually, a system of spherical particles, disks in 2 dimensions or spheres in 3 dimensions, interacting via excluded volume effect, but that are intrinsically self-propelled. And because that's the simplest system in which I can actually address this issue of the interplay between self-propulsion and steric repulsion. Now, clearly, many active systems are at high density. You saw Lisa Manning's lecture on Friday. The cell layers she was discussing were a very high density. In fact, they are what one calls confluent. There are actually no gaps between cells. There are many other systems that are at high density. And just for fun, here is one. Okay? Imagine looking at these penguins from above and look at the cross-section. They are like disks, right, roughly. And they interact with each other. They form these dense huddles. And these are actually, this is work by a group in Germany. These are emperor penguins in Antarctica. But the most interesting thing to me is if you look at a close-up of the densely packed huddle, see up there, what you're seeing there, I would say, are phonons in your penguin huddle. These penguins are actually making some small displacements of their feet, but while staying roughly in space. So they're active in a very funny way, in a very simple way, if you like. And there is these collective waves that propagate through the system. And what the collective waves actually do is make the huddle more packed, as a matter of fact, so that they can actually even keep warmer. So dense active systems. And the very first thing we want to do to discuss dense active systems is actually to understand a little better the difference between Brownian dynamics and what I will call self-propelled dynamics, and also the run and tumble that I mentioned last time. Now, I mentioned last time now a much simpler synthetic active systems, which are these active of self-propelled colloids. So these are experiments by the group at NYU. This is a paper by Palacci and others that appeared a couple of years ago in Science. What the experiment sees, and I don't want to go and tell you how really it works, but these are colloids about 600 micron in diameter, I believe. They have a little cube of hematite immersed into them. They're really plastic colloids. They have a little ball of hematite, a little cube of hematite immersed in them. When they are in hydrogen peroxide, the hematite, like the platinum gold colloid I mentioned on Friday, the hematite catalyzes the reaction of the breakdown of hydrogen peroxide, but it does so only when you shine UV light on it. So this is a very nice active colloid system because you can actually control whether these are Brownian colloids when there is no light, or active or self-propelled colloid when you shine light on them. So that's what this movie is going to be about, and the movie is going to show you when there is light and when there is not. And what you're going to see is when with no light, you're going to see Brownian dynamics, and this is a big particle, so they're just going to be shaking around a little bit, not going very far. And when the light is on, you're going to see them behaving like self-propelled particles. So now they're just Brownian, and now the light is on, and they move around as self-propelled particles, and this is kind of a sketch of the kind of trajectory they perform. And it's somewhat different, but as we will see, not too different, but the type of motion that E. coli performs, this run and tumble motion, where you go in a straight run for a little while, and then about once every second, you do a tumble, you spread out your flagella, and change the angle by a big amount. So both cases, we have sort of ballistic dynamics interrupted by changes in angle, changes in direction. In this case, the changes in angle are large and discrete at some rate, which is distributed with a, say, exponential probability distribution. And in this case, the change in angle are continuous and small. And I want to kind of tell you a little bit more about the details of these dynamics, because that will be important in understanding the role of steric repulsion in this system. Just one more thing, some of you may have seen this, when you actually put together many of these colloids at high density, self-propelled particles without attractive interactions can actually form clusters and even phase separate. And that's precisely what I want to talk about and show you a simple model that actually describes this. It's not depletion. That's exactly the point. It goes away if you turn off. Did I show that? Sorry. OK, light is gone off, and see it goes away. It's going. I'm going to erase while you watch it. OK, so let's do that. It's probably looped, right? Can go on forever. OK. Not nearly as nice as when you start out, but. OK, so I want to talk about the self-propelled dynamics. So last time we mentioned Brownian dynamics. So if you have an overdamped Brownian particle, write a Langevin equation to describe its dynamics. We write V equal dr dt is just equal to noise. If this is a Brownian particle in equilibrium, this noise is a zero mean, is white and Gaussian. With correlations we showed last time, determine let's say we are in 2 dimensions, okay, determined by fluctuation dissipation theorem that says that D is kBt over zeta, where zeta was the friction. And if we calculate the mean square displacement, where delta r of t is r of t minus r of 0, we get diffusive behavior at all times, because we have assumed overdamped dynamics. Or if we had not, we will get diffusive behaviors of time long compared to the mass divided by the friction. Now, what about a self-propelled particle? One of these active colloids. Let's write the equation of motion for the overdamped dynamic of a self-propelled particle. So the velocity, we're going to write it as self-propulsion speed. Again, this E is the same. We are always in 2 dimensions here. The E is a unit vector with the x-axis. And then we can add noise, which we can choose having the same correlation. So there is noise in the translational equation. And the angular dynamics is just noise. And the zeta has also 0 mean. Is white and Gaussian with correlation delta r. So d is a diffusion coefficient with dimension length squared over time. dr is a rotational diffusion rate with dimensions just 1 over time. It's just a frequency. Okay? And these my equations may describe the dynamics of one of my self-propelled colloids. We can calculate the mean square displacement here. And this is an exercise, homework. We can calculate exactly the mean square displacement of one of these self-propelled colloids. And if you have never done this, I know Michael has done it and Giuseppe has done it, so ask them, get some help. But this is actually a very simple exercise and something you can do exactly. And what you find is the following. This comes from the same place as that one over there. And then we have this other term, V naught square divided 2, OK, I'm going to put the number 2 V naught square divided by dr, t minus 1 minus e to the minus t dr divided by dr. So it's an exact expression for the mean square displacement. Now, what's the behavior of this term? Let's look at this term here. OK, this term, if t is short compared to 1 over dr, you can expand here. And what you'll find is that this term goes like v naught square t square. The behavior is ballistic. These particles travel ballistically with speed v naught, not surprisingly. If t is large compared to 1 over dr, this term over here goes like v naught square over 2 v naught square over drt. Okay? That is, the contribution from this term is also diffusive. And if I put everything together, 4 times large compared to 1 over dr, the whole thing goes like as 4 d plus v naught square over 2 dr t. So we have, if you like, an effective diffusion coefficient, which is composed of 2 pieces. The original translational diffusion that we had in our, even in our Brownian particle, and another, let's call it active or diffusion coefficient that comes from the cell propulsion. It's actually very easy to understand this second diffusion coefficient. Well, first of all, dimensionally, you could just have guessed it, as a matter of fact. But in addition, if you think about the dynamics of one of these propelled particles, the picture I showed you before, we can actually define a length scale, which is a persistence length, very much like the persistence length of polymers, which is V naught divided by dr. And so then this, let me call it SP contribution to the diffusion coefficient, will just be the square of the persistent length, which is the length scale over which the path sort of remains straight, if you like, times the rotational diffusion rate. Okay? So a self-propelled particle seems very boring. A long time, it's diffusive, just like a regular Brownian particle, although its diffusion constant is enhanced by this piece over here. Okay? D is defined like above. D is defined above. D is defined above. Okay. And in general, by the way, in a thermal system, I mean, suppose you had a ellipsoid Brownian particle. Okay. Then you will have also there you'll have translational diffusion and rotational diffusion. And in a thermal system, the two will be related because they're both proportional to kT. The translational diffusion will be roughly of the order of the size of the particle squared times the rotational diffusion. Okay. In the case of active particles, whatever drives the system is not thermal, so in general, these two quantities are not related. We could assume that the translational diffusion is of order kT and the rotational is not, which is actually often the case. Or we could assume neither of them is of order kT. Okay? And let me just say one more thing, because I need to take a break. If I had done this, so this sounds boring. If I had done this for a run and tumble particle, it sounds even more boring, because actually these would go through pretty much the same, with the only difference that for up to perhaps a factor of 2, for a run and tumble particle, dr gets replaced by the tumble rate alpha. So the details of the angular dynamics don't seem to matter very much. You get pretty much a similar diffusive behavior at a long time. Okay, so we're taking a little break, and then we'll see how this is actually not as boring as it looks. Yes. Okay. No, I don't think so. I think I've got the factors correctly. But
LP squared dr. It's phenol squared dr. Over dr.
I have a 4 in front because in 2 dimension, the diffusion is defined with a 4 in front.
Okay.
Do you want to ask a question? So I have some confusion about these terms. Like in John's lecture, it was.
What's that?
So
Sorry.
in John's lecture, it was positive, and so this was trying to propel the particle, and this was trying to reduce it.
Because it was described in the order state. Yeah. The order state happens when alpha is negative, right?
Yeah.
And alpha John Toner.
It's minus. Okay.
There might be some factors of rho in that as well because your W is your V. But
I know. But alpha actually doesn't matter because it's alpha doesn't matter.
Beta
So and same for beta.
Yeah, this should be plus.
Yeah,
So that's what
it was
I was
confusing here above.
From this.
Yeah. So then everything makes sense.
Oh, you're right. Sorry, I had also the wrong sign. Yes, thank you. Okay.
One of the problems in this field is that everybody uses slightly different notation, and including me, between different papers I use different notations. So you have to keep your wits about you. But it's the same thing.
Yeah, but let me erase this so then I can, or maybe I can erase with the water.
Similar changes sign lambda.
Certainly this one, please.
This one?
Yeah, I'll think about this one. What's that? Yeah, please erase that. Please that one. I'm thinking about this one. I think I will erase this one. You can erase this one too. Just leave that.
Okay, those two.
This one.
This one and
Yeah.
that one.
And both of those. Yeah. Yeah. Thank you. Yeah.
For your random walk analogy, the bacteria seem to be, their tumbles seem, if they're not correlated at all, then it would be a very flexible system, right? Like.
Yeah, you mean the path would be like very flexible polymer, that's what you want to say.
It seems like it would be, it almost would have no persistence, like other than just, it would be like a random walk.
Well, but there is a persistent line because they actually, so they still tumble only once a second. Okay. And they actually go in a straight line.
Okay, so they are rigid.
So it's like, okay, then maybe you're calling this the persistence length. You would call it the length of the monomer.
Oh yeah, I got
okay.
No, yeah.
Maybe or something
so
like
it's
that.
The discreteness scale. Yeah.
But it doesn't matter if you actually calculate. You can do this calculation in both cases, and that at a long time it doesn't seem to matter for these.
Cool. Thanks.
Yeah.
Now the question is, if one goes great with higher orders, does one pick up just that term, or do other terms observe the rotational field?
Yeah, you'll pick up other terms, but you won't pick up.
So what time? At what time? I only have like half an hour left, right? No. What is this? Half an hour.
Sì, 45 minuti. No, vabbè, se hai bisogno di un po' più di tempo.
No, it's okay.
Oh yeah.
You'll get things like that, but that's not your business. Sure. So the only thing you can get that have.
So I missed like one at the start. So when you had this, and then you define these moments.
Yeah.
I wasn't sure. How do we get here?
You integrate over angle. First one integrate over angle. Second one you multiply with E, and integrate over angle. You take the moments.
This equation.
Yeah, you do that. Yeah, you multiply with E, integrate with angle. You get an equation for W.
So So I guess I just like, oh, this integrate over angle, that's what gets rid of this second derivative.
Actually, it doesn't get rid of it, so you have to try to do it. And
Okay. So I should work
you have to do it. Yeah. Let's start again. Okay, so let's continue. All right, so that's a mean square displacement. And by the way, I want to do a further actually simplification here. So here we go with homework 2, okay, which is actually estimate the value of the translational thermal diffusion coefficient of a Brownian particle. And this thing I call the DSP, which I said is V naught squared divided 2dr in 2 dimensions for, say, a native colloid. Now, how are you going to estimate this? For a native Brownian particle, colloid, Brownian colloid, how are you going to estimate that? Right, okay, so you're going to estimate that, you're going to estimate this. And what you should find is that this term, so this is always much, much smaller for whether you put in values for a colloid where V naught is of the order, say, 10, 15 micron per second, or E. coli where it's always also 10, 15 micron per second. Or you put in a rotational diffusion rate for a colloid, which is also of the order of 10 to 1 inverse second, or 10 to the minus 2, maybe 10 to the minus 2 to 1 inverse second, or the tumble rate of E. coli, you'll find that this is typically at least 100 times bigger than that one. And that is why often we just neglect this. We neglect noise in the translational dynamics, and we just consider the rotational noise in the angular dynamics. Okay? So we end up at the level of one particle. Then we have a very, very simple model here. Now we are going to neglect this, throw it away. So we actually have a very, very simple model that we can, of course, solve exactly. There is one more simplification, sort of a nice connection we can make at the level of one particle, which is the following. We can take those two equations, we can integrate the second equation, and put it in the first equation, formally. So formally, we can rewrite these two equations as just one equation for the position, and some new noise, I'll call it psi of t, where psi of t is V naught E, if you like. And the correlations, you can show that the correlation of this noise are given by the following expression. They are V naught square e to the minus dr t minus t prime. Square, I did say square, don't I? V naught square e to the minus dr. So in the limit, of dr going to infinity, this actually goes to v naught square divided dr times the delta function. In other words, for finite dr, our one self-propelled particle model is really equivalent to a overdamped particle with non-Markovian noise. And the non-Markovian noise comes up on scales 1 over dr. And in the limit of very large dr, it becomes a thermal-like system. And in fact, you can actually, at this level, identify an effective temperature. And the effective temperature for this one self-propelled particle comes out to be v naught square divided 2 mu dr. Okay, where mu is the mobility. Mu is 1 over zeta, is the mobility. So it looks like we could describe this as a thermal system. And now, by the way, now you see why. And indeed, you can actually calculate the pressure of an ideal gas. Let's say there are not many of these particles, but there are no interaction. So the pressure of an ideal active gas will indeed just come out to be rho kBT effective, if you actually calculate it, provided your system is really very, very large. Maybe it'll come, because actually an active gas in a finite box will have clearly a pressure that depends very much on the size of the box. Because if the persistence length becomes comparable to the size of the box, then the size of the container really, then the dynamics is ballistic, no longer diffusive, the way I've described it here. And then the pressure has a different value that actually depends on the size of the box. Yes?
What is mu in terms of the parameters of the initial pair equation?
Is the mobility, so is actually, you would have to start, you have to go back. Okay, mu, this V naught, you have to go back and think of this V naught as a mu times the self-propulsion force, if you like, okay? Where mu is 1 over a friction. And there is actually something really peculiar that comes in here. So you really should have started with a massive dynamics and then taken this limit. And in the massive dynamics, you would have had a friction or a mobility, depending which way you put it in. And the issue is that mu dr actually has dimensions of 1 over a mass. And so you need something in the model to take place, to provide the unit of mass if you want to define a temperature. And that's how it comes in. Okay, so thank you. That's really how. Okay, now this is all very nice. It's very tempting. So you're saying, okay, so these are just boring. These particles, you can just describe them as in terms of an effective temperature, and that actually this is really not quite the case. It's true at this level, just one particle at the level if you're just looking at diffusion. But actually, you can show that, so normally the notion of effective temperature can be very useful, has been, for instance, very useful in the context of glasses. And the way it is usually introduced is if you are in equilibrium, there's a fluctuation dissipation theorem that says that the ratio of a correlation function to a response function is KT. So when you're out of equilibrium, there are systems in which the ratio of a correlation function to a corresponding response function does not depend on the particular field to which you're coupling, on the type of probe you apply to your system, and therefore this ratio can define an effective temperature, for instance, in glassy systems. Unfortunately, this kind of relation will hold here, but actually has been shown to fail either at high density when you have interactions among the subpropelled particles, or sometime even at the single particle level, where you actually may get a different definition of the effective temperature depending on the applied force. For instance, if you confine your particles by a trapping kind of potential versus looking, say, at a sedimentation problem, you actually get different definitions. So this is very nice. It's nice for the dilute case, but it really doesn't work all that well in general. So we're really not going to use it all that much, but it's a nice analogy here. Now, I don't have a lot of time, so I want to at least tell you about, so far, diffusive, effective temperature, nothing terribly interesting happening. But something interesting actually does happen when you put many of these particles together and they interact with excluded volume. So what we want to do now is take many particles. We are going to neglect translational noise, but we're going to have many particles. So I'm going to put a label I everywhere that labels particles. Here, here, here. There'll be J, I guess, and I need to add a delta J, okay? And I'm going to add interaction. And now I will put in a mobility, 1 over a friction, and I'll put in some interaction, some forces. I'll call them Fij. And these are just repulsive forces, okay? And you could choose them. Actually, people have looked at this kind of problem using hard repulsion, hard spheres, hard disks. This has been done in about 2 and 3 dimensions. So hard repulsions, WCA potentials, soft repulsions. I'm going to show you some images that refer to soft repulsion. And by soft repulsion, I mean that we have disks, right? We have 2 disks of some size. And when they overlap, if they overlap of an amount delta, there'll be a force, a repulsive force, simply proportional to this overlap, which is directed in the direction of the colliding center. So sort of like springs. This is kind of the softer repulsion you can make. But I'm going to show you some results that actually do not depend. It has been shown that what you find about these particles actually doesn't depend on the type of potential you use. Yes, it does. And in fact, well, let me show you, and then I'll tell you. Absolutely, it does. And so what you actually find is that they phase separate. So there is no attraction. We know that particles with attractive interaction, or for instance, they phase separate. But these are particles with just repulsive interaction, and then can phase separate. So these are actually simulations that were done by Yao and Philly a few years ago for this soft spring-like potential. And if you look at this column here on the right, though the color indicates clusters, okay, these are 2 different packing fractions. Packing fraction is the fraction of the area that is covered by particles. So pi a squared times the number, if a is the radius, times the number of particles divided by the area. And what you see that at above some packing fraction, there is a dense cluster here, which is actually not a solid. It's like a very dense liquid surrounded by a native gas. And what this is for comparison is we compared with a thermal system, where the thermal system was defined in the following way. We chose the temperature such that temperature will lead to the same kind of overlap as cell propulsion. So that's how we defined an effective temperature. And the thermal system, they show some clustering, of course, at high density, but clearly does not phase separate because there are only repulsive interaction. Let me just show. So these actually also were polydispersed particles for no good reason other than that's what we had started to work with. But people have done this also for. Actually, there is a reason. The reason was that we were interested in glassy states. And in 2 dimensions, monodispersed disks don't form glasses. And so that's actually why we were working with polydispersed particles. So let me show you a movie corresponding to that big cluster. So these are your active disks. The arrows are the velocities. And you see these big clusters. Of course, in the other image, these are periodic boundary conditions. So in the other image, we had taken the bottom piece and glued it up there to make a nice big cluster at the center. Here, we did not. So there is this phase separation. That's right. So these are the penguins. Exactly. The penguins really do. I don't know. I've never really looked at them from above, but my feeling is that they must look like disks from above. So maybe penguin may have attractive interaction. So in fact, that's an interesting question. What happens to this system if I also add attractive interaction? And actually, Aparna Bhaskaran at Brandeis has done some nice work on this. I don't think I brought an image, but there are regimes in which actually the attractive interaction can lead to, instead of leading to complete phase separation, there is actually more clustering, or even what looks more like gelation, actually, I would call it. So the system looks more like a system undergoing gelation. So you get more complicated kind of interesting patterns. And yes, the penguins may have attractive interactions indeed, but I will just.
So that's not a solid, but
Well, these were because of all the dynamics, and also if you actually look at the mean square displacement of just particles in the big cluster, you will actually find that the diffusion coefficient is very slow, but is very small, but is non-zero. Okay. Now these systems do form glassy solid states, but not yet here. Okay. So I really think one should think of it as a dense liquid in a gas.
I mean, the fact presence of single particle diffusion doesn't rule out the possibility of it being crystal.
They also, the systems also form crystals, but I'm going to show you a phase diagram in a minute. Okay, so that's,
12/6 probably is pretty high.
yes, yes. And also the other thing which this doesn't show is that actually there is a lot of ordering. So here, most of the particles are pointing in, right? I mean, this system does not order in a flocking state because there is no alignment interaction, and the things are disks, so there is no orientational order due to steric effects, so you don't get a flocking state. But actually, you can get quite a bit of ordering, and at this boundary, it has been shown that actually a lot of them are kind of pointing in. In fact, one simple way to understand why this happens, I wanted to actually work through a little calculation, but you can do a very simple kinetic argument. Well, first of all, this will happen, I should have said, only provided the rotational diffusion is sufficiently slow. Because if the R is very large, indeed this system looks thermal. If the R is small enough, essentially when particles collide, they stay there long enough that they see the clusters. Essentially, this can happen provided 1/r is long compared to the mean free time between collisions. And so that will give you a criterion for sort of this phase separation to happen. Okay?
And the phase separation, if you make the system bigger, keep all the parameters the same, the cluster you form, we always phase separate into one big cluster.
Bigger, more particles. Yeah, you will get, and you can actually do even, there's been a lot of work on this. Perhaps only the only good reason is that this is a simple system, okay? there has been almost more work than it deserves, I would say, for the reason it's a simple system. But you can actually go quite a long way using free energy analogies and van der Waals and identify a spinodal line, identify binodal line, and all of that, okay? And sorry, I know this is a question, but I reminded that I was going to say one thing. So what is this system, why is it so simple? It's simple because if you think about it, the angular dynamics, the single particle angular dynamics is decoupled from forces and from the other particles' angular dynamics. There are no torques here. Particles don't experience any torques. As soon as you add torques, things get a lot more complicated. So when you ask me about the centrality of the interaction, yes, that is key.
No, the motivation for my question was just, I was wondering whether, there's a characteristic time associated with rotational diffusion. I was wondering if you translate that by multiplying it by B naught into a characteristic distance, and the scale of these clusters would be set by that distance. You're saying no, that's not the case.
No, it's not quite. It's not quite like that. And there is, by the way, yeah. Okay, that should answer. Yeah, yeah.
You see lots of things flying on and off the interface.
Yeah, they.
Set by their distribution factor.
Yes, that's right.
Are there funny fluctuations of this interface strain signature?
There have been one person looking at those and claiming not really. So probably, maybe not.
So you have two effective temperatures. Why is
No. This temperature is, okay, so this model I wrote down there, okay? Actually, I should have erased everything else here. Erased. I do hope people wrote down the homework though, because it'll be checked. Okay. So this is a simulation of that model. Okay? Forget the effective temperature. Now I'll get to the temperature. These are Brownian particles, that is, forget this equation, forget this piece, but add thermal noise here. Okay? So what the other column is, I should have actually erased the other column, but I didn't. So the left column, okay, are simulations of the following system. Okay, where this eta, okay, let me just do this. Okay? And this T equivalent is chosen by estimating it as giving you the same amount of overlap as a cell propulsion would. Okay? So these are just Brownian particles at some temperature, and these are the self-propelled particles.
So you've tried to make this column on the left as similar as possible to the column
Yes.
on the right.
Yes.
And what you're showing is that
Yes.
non-equal
The dynamics, this difference in the dynamics that looks very innocuous at the single particle level is just diffusive. It actually makes a big difference here. That's the message. Okay. No, there is no rotational diffusion here. There is no DR. There is no DR. This is, so the left column is this model. This is the right column. And DR is very small. I don't know, forgot. Okay? Oh, it says that. It's very
You just construct another effective temperature, V naught square over.
yes, but I also told you that effective temperature doesn't really work when you look at many particles. So, okay, if I estimate that effective temperature in this case, that effective temperature, I believe, is about 10 to the 4 degree Kelvin. It's a huge number. If you estimate that effective temperature for these parameter values, it's a huge number.
So the cluster has a temperature, and outside the cluster, that's not temperature.
If I estimate that effective temperature,
Yeah, for the cluster.
that effective temperature works at most for describing the properties of an ideal gas.
But there is gas, right? You have cluster
Here,
and
maybe here. Yeah, maybe you could, okay. So what you're asking is whether I could describe these as two effective temperatures. Maybe I could, but I don't think it's very useful. I mean, it's, okay. Yes?
So the transition, the 5 state that you've written there is 0.4.
That will depend on the R, and they will,
yes.
I mean, yeah.
Yes. So what sort of transition is that?
It's a spinodal line. It's a spinodal line. It's a phase separation. So in fact, we actually constructed phase diagram here. I'll show you phase diagram. So let me just say, I would like to go through one simple argument to explain this. I'm not going to have time to do what I plan to do, but so the phase diagram, just very quickly, cell propulsion, packing fraction, homogeneous liquid, phase separation, and actually a glassy state as well at high density. And I'm not going to say much about any of those because I just want to try see if I can work through, give you a simple explanation of this phase separation. Okay? And this has been verified for other potentials. And by the way, the phase separation at high packing fraction, a lower packing fraction is dense clusters in a gas. At high packing fractions, these holes in a dense surrounding. Okay. But any other question? I just want to see if I can work through one simple way of understanding this. Actually, let me just say it from the outset. So what's happening here is really very simple. You're self-propelled. As the system gets crowded, your self-propulsion speed, there'll be some effective self-propulsion speed that goes down, right? As the self-propulsion speed goes down, in regions where the self-propulsion speed goes, in the high-density region where the self-propulsion speed goes down, the density goes up, okay? And so there is a feedback between these two effects that actually leads to this phase separation. But let me show you this by a very simple calculation that is actually was done a long time ago in 1993 by Mark Schnitzer in the context of E. coli. He was looking at one-dimensional run and tumble. Now, in one dimension, actually, there's really no difference because rotational diffusion has to be the same as run and tumble since you can only go right and left. There is not much else you can do, okay? But he looked at one-dimensional run and tumble where you have a run speed, so just one particle, or many non-interacting particles. Actually, let's think of many non-interacting particles. You have a run speed that depends on position. So somehow your medium is inhomogeneous, whatever. And then you have a tumble rate, which is constant. Okay? And in one dimension, many non-interacting run and tumblers that can be going right or going left. Let's describe this phenomena. So let's denote by R of x and L of x the density of particles that are going right, left. Okay? And that just write down equations for their time evolution. So the dynamics, the R, the number of right-going particles, can change because of convection, because because they're self-propelled at this speed v. It can decrease because they tumble to the, it can decrease if they tumble to the left, and it can increase. R. What am I doing? R is the density of particles moving right, and L is the density of particles moving left. So it should be R, and this should be left. Okay? And similarly, the L dot is minus dx of VR plus alpha over 2R minus alpha over 2 left. Okay? It's very simple dynamics. Let me actually rewrite these equations in terms of a density, right plus left.
So that should be L.
Yes, sorry. Yes. Let me rewrite in terms of a density, R plus left, and the difference, R minus left, which is sort of like a polarization, if you like. If I were in 2-dimensional, 3-dimensional, that would be the kind of quantity I would call polarization, is the asymmetry, the excess of right going. This is sigma, if you're asking what that, what that is. Okay? Now I can rewrite these equations in the following form. dt rho is minus derivative with respect to x of v sigma, right? And dt of sigma is minus
the equation working for L.
Oh, here. Yeah. Minus alpha sigma plus dx v rho. Okay? You can just play around with these equations. Very simple. You can rewrite them like this. But I want to point out, now, think of this sigma as a polarization, sort of like my W before, or John's V. Okay? This is by conservation law. Of course, density is conserved, so this is the only equation. This is the current, tumble rate, times this effective velocity of polarization. I have the decay. Sigma is not a conserved quantity. It decays at the tumble rate. In my equations, I had dr here because I was doing continuous diffusion. Here I have the tumble rate. And then there is this term, which is the convection, if you like, of the polarization, just like I had in the continuum equation, more general continuum equations. Now, if I'm interested in a time, and of course you can actually do all of these in higher dimension, but it's nice to just do it in one dimension. Now let's think about two things. First of all, if I'm interested in a time large compared to 1 over alpha, okay, I can actually neglect the dt sigma over there. So I can write sigma approximately given as plus 1 over alpha dx of v rho. I think I have some wrong signs. Yes, that's supposed to be a minus. Because I know it's supposed to be a minus in there. Okay. And then I can substitute in the density equation So I'll get minus dx minus v over alpha. Where is the density equation? V over alpha. Dx of v rho. Okay? And I can rewrite this, actually, as a diffusion equation with an effective diffusion coefficient, which I don't seem to have written, but what did I do? Whatever. Okay, I can rewrite this as d effective, that of course depends on position, dx of rho. Okay? Yeah. Yes. Yes, essentially it is. That is why I didn't really, okay. And, but let's just look at this equation a minute. Suppose we look for a steady state solution, for a steady state solution. Steady state solution means we are going to assume that the density doesn't depend on time, and then this thing has to be 0. This is really a current, right? So steady state solution says that dx of the current has to be 0. That means the current has to be constant. But if there is no particles, we are not driving the system from the outside, the total current, this constant must to be 0. So the current must be 0. Okay? So let's set that equal to 0. So what we get, well, the alpha is a constant, so we can throw it out. So we get minus v.
So there's actually a second term here. You can let the x derivative.
Okay, so I was trying to, I don't have time, so you, okay. No, you can do it. Okay, I know what you want. I know exactly what you're looking for. So we can rewrite it the following way. Okay, let's rewrite this equation in the following way. We rewrite it as minus derivative with respect to x. We have minus v squared over alpha dx of rho, okay, minus v prime, the prime means derivative with respect to x, over alpha rho, okay? And this is my current. And the reason John wanted to write it this way is because what we have here is like a diffusive current and a convection, okay? And the convection is non-zero only provided v depends on position. If v is a constant, this term goes away. You just have diffusion. But if the convection is non-zero, so normally you will write a current as minus, say, some diffusion coefficient dx of rho plus the convective velocity times rho. And by comparing these, you can identify a convective velocity depends on position and the diffusion coefficient over here. Okay? So now I go back to my argument. I look for a steady state solution. The derivative of the current must be 0. Okay? But this is not a driven system, so the current itself must be constant, but the constant must be 0. So I set this current equal to 0. So I set minus v squared over alpha dx of rho equal to minus v prime over alpha rho. Clearly, alpha is a constant. I can get rid of it. I can get rid of a factor of v. So what I end up with is an equation, see if I did it right. I think I did it right. That just says that 1 over rho dx of rho is minus 1 over v dx of v. Okay? And I can solve that equation. Say rho of x, rho naught, and I have v naught, which is the velocity at some position, divided by v of x. So the point here is that while diffusion, as John reminded you, if you have a diffusion equation, the steady state solution of the equation, if you have a local density fluctuations a long time, the steady state solution is that the density is constant everywhere. This system is kind of strange because it does the opposite. The homogeneous solution is not constant. The density is large where v is small. Okay? Now, if you were to do this in a many particle system, with or without interaction, assuming at the beginning a constant self-propulsion speed, so not a self-propulsion speed that depends on position, by taking into account collective effects, what you would find is a similar solution where instead of the effective cell propulsion speed actually becomes a function of density. And so you actually get that you have a system where the density goes like 1 over the effective mean field, if you like, cell propulsion speed that in turn depends on density. And these can be calculated at least perturbatively in the density. It will involve pair correlations of the particles and things like that. But the point now is that there is now a feedback here. Whenever density is high, and to leading order, this V of rho goes like V naught, 1 minus lambda rho, where this lambda is a parameter that depends, for instance, on pair correlations in the system. So whenever the density is high, the effective cell propulsion goes down, but then the density goes up in that region. And this feedback effect is what leads eventually to the phase separation.
So basically you're saying this equation has two self-consistent solutions.
Yes.
One is the high density, one's the low density.
Yeah. Yeah, sorry.
So
No, I think.
can you think about it like a particle moving on a terminal orbit?
So it's really quite different. Here I was showing you a simple model where you just have a particle moving with a so it's different from an external potential, because an external potential, I don't think, will give you these at high density, okay? So at the single particle level, there are other ways of constructing this kind of behavior, yes.
The other example you can model is the V of X.
Right. So that's what I want to say. These you can certainly think of as a particle in a potential at the single particle level here, okay? But these you cannot. And this I was just using it to motivate writing that down, or actually I was planning to derive the equations, but whatever. I will not.
It's more like simple model of traffic dynamics.
If you want, it is.
Typically a front or a shock here.
That is true, yeah. And let me just say, absolutely. Let me just say that there has been a lot of work on these systems. As I say, Mike Cates has done a lot of work on these, and his collaborators connecting it with some, he has developed an effective free energy type description of the phase separation. More recently, us and others have calculated the pressure exerted by an active graze on the walls. And it wasn't obvious from the beginning. So, normally in equilibrium, what's the pressure? Pressure is force on a wall per unit area of the wall, or is minus the derivative of the free energy with respect to volume, or you can calculate it from the hydrodynamic stress tensor using Irving-Kirkwood type formula, and they all agree. It wasn't obvious this would be the case in these active systems, and in fact, it turns out that all these, well, we don't have a free energy, so let's forget that definition. But the other two definitions, force on the wall and calculation from the stress tensor, can be shown to agree, provided you include in a new piece of the pressure, which is this active or swim pressure that the particle exert on a wall just by virtue of the fact that they're swimming. But as soon as you go away from a simple model like this where there are no torques in the dynamics, things are more complicated, and actually is possible. There have been suggestions that in that case, actually, the force on the walls may, these two definitions of the pressures may not agree, and the pressure exerted by active particles on a wall may actually depend sometime even on the properties of the wall, how soft or hard the wall is. And so there's a lot of work going on these things right now. Yes.
Because you can't really define an equation of state.
Right. Which means that you cannot really define an equation of state. Yes, absolutely. Okay, so I will stop here and go on tomorrow. Okay, unless there are more questions. Thank you. I'm going to wash my hands first. Yeah.
I don't see why J has to be 0.
Well, because it's a there is no source of sink in the system, right? So there is no mean currents, and it's not equilibrium. It's a steady state that is not going.
But I'm thinking of like the steady state in the Toner 2 equations, where the homogeneous.
But this is one particle.
This is one part.
I mean, or many non-interacting particles. So there's nothing.
So then J should be 0. Okay.
That's all. So, yeah. Yeah.
Were you referring to works by Yariv Kafri and other people, for example, on the active pressure?
What's that?
Were you referring to works by Yariv Kafri and Maren Carter about?
Yeah, well,
the active
actually, we are the first ones who calculated the active pressure. But yes, there is also all this work they have done, and there's been a lot of work. Right? There's like a new paper every week on this active pressure. Yes. But
okay.
no, I mean there are some very nice. There are two very nice papers that came out recently. In both of them, the first author's name is Solon, S-O. Alex Solon. One, I think, was published in Nature Physics, and one in PRL, I think. And so if you want to read about that, I think those are very nice.
Okay, and when you go to the functional limit,